Who I am. My name is Riley. I'm a heavy equipment instructor, and I'm going over and doing a mini series on alternators, how they work, how they function, what makes them tick, testing the individual components, the overview of the alternator itself. And today we're going to talk about the diode rectification bridge, what the faults in our rectification bridge look like if we're diagnosing or troubleshooting our rectification bridges, if we have this alternator disassembled and pulled apart, how we're going to use a multimeter to test those diodes. I'm looking for any one of the three diode conditions that we may see. First of all, what is a diode? An electrical one-way check valve. So a good normal operation will be flow through a diode in one direction and no flow in the what we call reverse bias or opposite direction. Okay, and then the two bad diode effects, which could be a shorted diode allowing electrical current to flow in both directions, or an open diode allowing current to flow in no direction, essentially opening up that circuit. So I drew today, I have the diode rectification bridge. Okay, I've got my 6 diodes outlined within my rectification bridge. I've got a Y-type stator in this instance. For our diodes inside of our rectification bridge, we're going to have 3 diodes in 2 different groups for a total of 6. Okay, we've got our positive diodes, okay, allowing the current from our stator outputs out to our battery and to run our electrical loads. Conversely, we have our 3 negatives, or the return path. Okay, that puts those 3 diodes in the forward bias to the return or the ground, and my 3 positive diodes will be in the forward bias for my output, the current induced in my stator. So the effects of a regular diode, at any given moment, we have to appreciate the speed at which this is all taking place and that this is happening. But if I was to take a snapshot of this particular alternator's operation, at any given moment, I'm going to be acting on 2 legs in series in this alternator. So if I'm inducing a stator with my rotor, this is my rotor coils. We talked about in a previous video the 5 factors that are going to determine how much current is going to be induced. Go check that out if you don't know what I'm talking about. We're going to induce current into these stator legs, or phase windings, I sometimes call them as well. That current is going to be an output on one of these 3 legs. So if I'm going out on this leg here, that current is able to flow. Because it's a positive current, it will deactivate this diode or put it into the not allowing flow function. It will open up this diode because we have it in the forward bias relative to the current flowing through the circuit. It will open this diode. Okay, now we've opened this diode. We're on the anode side of this diode. It's not going to open up these diodes. These diodes are going to be deactivated. That current will flow out, charge my batteries, maintain my batteries, put a current through my batteries in the correct orientation, run that current through any electrical loads, and go back out to ground. At which point that ground, through the internal case of my alternator, will have a path back through these negative diodes, whichever negative diode I'm acting on in series with. So let's say I'm utilizing this diode. We're going to return through ground back through this diode in on that negative side. Okay, so that completes that circuit for that given snapshot of a moment in time on this alternator. If I was to choose 2 different legs, let's say we're going to induce a current and go out on this leg. Okay, it doesn't really matter to me which leg we go out on, and we can return on either leg. Okay, so we'll go out, this diode will shut off, it's a positive flow, will flow through. These 2 diodes won't allow that flow through. It will go out to my electrical loads, charge my batteries, run any lights, run any electrical loads, whatever those look like in your given instance. And then go back to ground, at which point it will flow back. And I don't care which leg it flows back on. It can flow back in this leg and act on this coil. That's going to be what completes my electrical circuit for this rectifier bridge. Now, just let me clear out my messy green marker here. If I was to have an event, one of my diodes fails in either the open or the shorted conditions, that's going to give a specific fault. Whether that be for an open diode, we're going to see a 33% loss versus a shorted diode, which can see anywhere from a 60 to 70% output current loss. And to help illustrate that, let's pretend that this diode is in the open condition. It's not allowing flow in either direction. So if I pick any two legs, okay, I don't really care which one. Let's go out on this leg, and we'll return on this leg. So our current output is going to flow out. It can't flow this direction. Okay, that's normal. That diode is operating normally. It cannot flow out this direction. Normally it wouldn't be able to, but it's an open diode anyways. So that current is going to flow like normal. It's going to return normally as it would. So I have no effect on that given pair of legs in that. Out of those three combinations that I have, that is not going to be affected. If I try to go out on this diode and return on this diode, that current is going to flow out. It's going to try to go this way, but that diode is in an open condition and it will not allow that current to flow. And that's what yields me on an open diode my 33% output loss. A given pair will not function. Okay, and that's essentially what we're looking at here. That current would be able to return like normal. Now, if we go out on this leg and return on this leg, we'll go out. That current will flow out, go to my electrical loads, run my electrical loads, charge my batteries, do whatever it needs to do. It'll return, it'll come back through my ground circuit, and it'll be able to flow back in. An open diode will yield us a 33% loss. Now, if I change this up and we look at how the current behaves through a shorted diode condition, so it can go through in either direction. It doesn't matter to me. That diode is essentially not in place, and I have just continuity through that conductor. Now, again, we have to appreciate how fast this is actually happening. We're just going to look at any given snapshot. We'll go out on this coil. I don't really care which one you choose, and we'll return on this coil. We're going to exclude the circuit with the shorted diode. Okay, so let's see what that looks like. Current is induced in a stator through the motion of the rotor. We rotate that rotor inside, induce a current. Current's going to flow out. It's going to flow through like normal, but when we get out of this first diode, it closes off this diode. That's fine, but that current is allowed to bleed back through and return. Now, electricity is like me. It's quite lazy. It's going to take the path of least resistance, and the path of least resistance is not going to be the electrical loads. It's going to be finding its way right back to ground. So a very large portion of that current will flow, and I don't have a definitive number. That's why we have a range of a 60 to 70% output loss. So that current will flow through. Some of it will go out to my electrical currents, run those loads in this given snapshot, come back on ground, and go through, which one did I draw it on? This one. But a large percentage of it's going to come through and short out that leg. Now, if we choose any other two given diodes, let's return on this one. Okay, and we'll go out on this one. So we're going to induce that current. It's going to flow through. It's going to approach this junction here. Can't flow this way because it's a positive current, and this diode's in the reverse bias. So it's going to flow out this diode here. It's going to flow out, and it's going to go out to my electrical loads. Alternatively, it has a nice, easy, short-circuited path back on that ground circuit. Now I'm supposed to be returning on that ground circuit, but I also have a nice, easy path on the positive side to just flow right through those coils. So on any of our three pairs of legs on this stator coil, I'm going to have output current bleeding back through the stator because of that shorted diode on any two of the given pairs. So that's going to yield me on a shorted diode my 60 to 70% output loss. That output loss is when we do an alternator maximum output test. So if I have a running piece of equipment, I load up that system, I'm looking for how many amps that alternator is capable of putting out. That's the loss I'm talking about. Now, this is all fine and dandy when I draw it on a circuit, but let's go onto the desk, we'll take a look at how to actually troubleshoot and how to diagnose a diode by using a multimeter and the diode function check. Here I have my Fluke 115 True Rams multimeter. This is my diode function check. The difference between my diode function check and my ohm meter check is the ohm meter check will tell me what the resistance value of that negative N-type material or the positive P-type material and their semiconductor material. That's not what I want for diode functionality. What the diode function test is going to do is it's going to induce or input a specific voltage, and that voltage value that we read when we do a diode check will be the activation diode. Or sometimes I call it the opening diode check. I don't like using that term. I'm trying to get it out of my vocabulary because it sounds like we're opening that diode in a failed condition. That's not what I mean by that. That's the activation voltage. Now that should be somewhere in and around the 0.5 millivolt range. So if I'm looking, I've got 5 rectification bridges here. I know one of them has a bad diode. I can't remember which one, but we'll take a look. We'll test them all. But first thing I want to do is I want to take that diode rectifier bridge. I want to identify which is my positive half and which is my negative half. Now, how I do that is I'm going to flip that diode rectifier bridge over. I've got 4 mounting bolts right there, right there, right there, and right there. You'll notice that 2 of those are utilizing this big plastic isolating shield from our case ground inside of our alternator. We're going to find which heatsink, well, what the heck's a heatsink? The heatsink are these big aluminum chunks of metal that are going to help to dissipate the heat that my diodes are going to release. They release a lot of high heat. These are high heat generating components. So they're attached to my heatsinks. These aluminum fins will pull that heat out and try and dissipate it out to the air that's being pulled through that alternator. So if I look at the back side of this rectifier bridge, whatever side has the plastic sheeting at the 2 bolt holes, that's going to be my positive half. That's the half that's isolated from my case ground. Okay, the other half up here, these bolt holes will go straight down through to my case. If I look inside, those are my diodes inside, those little black bits. So I've got one there, one there, one there, there, and there. There's my 6 diodes hiding inside. 2 of those diodes are going to be correlated to each output terminal of our stator, which will also be feeding my diode trio. Now this is the wrong diode trio for the rectifier. That should mate up nicely if I get one of my other diode bridges there. That fits on there quite nicely. Okay, that's the diode trio that supplies my input circuit from my output circuit. Okay, my stator is going to be feeding through that diode trio, a set of 3 diodes, and supplying my voltage regulator and my slip rings on my rotor to feed current to my input circuit. Now looking at this then, I've identified the lower half as my positive half. So now if I wanted to put those positive diodes in the forward bias, okay, that's going to be done by my multimeter leads. The leads themselves and the placement of my leads is going to be what puts these diodes into the forward or reverse bias. If I was to put this positive diode here, I'm not going to go on the terminal itself, I'm going to go on the little strap. Okay, if I put my negative there and my positive right on the heatsink itself, that's the other portion or the other contact point for that diode, that's going to be putting it in the reverse bias. And what I would expect to see for a reverse bias would be no flow. So on my multimeter, I'm looking, I still have an out of limits reading. I have no flow. Okay, I would go down and check all of my positive diodes with the same orientation. All of those are in the OL condition in the reverse bias. That's good. I want to see that. Now to put those positive diodes, these 3 diodes here, here, and here, in the forward bias, I'm going to take my positive lead, put it on the strap, and get my negative lead and touch that heatsink. That'll give me a very small reading. Now that is going to translate to a millivolt reading. 0.515 millivolts is what that is. Now that's the amount of voltage that is needed to activate that diode. That's going to turn it into a one-way check valve with that much voltage. That's good. That's a pretty good number. Anywhere in the range of 0.448 up to about 0.55 is pretty good range. I'll go through and I'll do that with all of these diodes. Perfect. I've checked that half of my rectifier bridge. My 3 positive diodes are in good condition. They're operating as electrical one-way check valves, allowing flow in the forward bias, disallowing flow in the reverse bias. Next is going to be my 3 negative diodes. Now the test is the same. The only difference is why my expected activation voltage will appear when my terminal leads are reversed. So if I go onto the strap with my negative lead and go onto the heatsink with my positive, that puts that negative diode in the forward bias. Go along, I'll do that with my 3 negative diodes. Perfect. Okay, in the diode function check, my multimeter should give me an audible chirp sound when it works. I can hear that chirp. I don't know if that's showing up very well. And then to check the forward or the reverse bias, pardon me, I'm going to reverse the polarity of my 3 leads. And I should have no flow in the reverse bias. Perfect. That's all we're going to do to test this rectifier bridge. This one is my messed up one. Okay, let's try this one. So this is, if I flip it over, right, I got my 2 isolating bits here. This is my positive half, so I know the lower half's my positive half. This will put me in the forward bias. Okay, they're all good in the forward bias. And the reverse bias, they're disallowing flow. Okay, we are in forward bias there, forward bias there, forward bias there. Let's go reverse bias. There's my shorted diode. So it's allowing, as I wiggle this around, I'm getting continuity in the reverse bias. That's my shorted diode. I'm allowing current to flow in both directions. Now with a shorted diode, that current draw through that diode is going to pull in a substantial amount of heat. I don't think that diode is going to stay shorted for very long before it decides to open up and burn up. We would still, with the shorted diode, see the 60 to 70% amperage output loss. And then from the open condition, that would change to a 33% amperage output loss, which would still be a pretty substantial loss. And we would identify that by doing a load test on the alternator. And don't forget to turn your multimeters off when you're done doing tests. Don't want to kill your batteries. That brings us to a conclusion on testing diodes with regards to our alternators specifically. I hope you found this video helpful. If I can help one more person, then I've done my job and I'm happy with the output of this video series. But otherwise, stay tuned for any more inspection videos for alternators. Have a good day.